Hey there. Hey, everybody. Welcome back. We're going to continue 12.2 in Calculus 3. We're looking at vector function calculus. We're going to do derivatives. Look at what the derivative is. Remember when we did f prime of x, we could do the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. This is the vector equivalent. We're going to do t plus delta t. You might have learned it as x plus h or t plus h here and having h at the bottom, h there, but I think delta t gives a little bit better picture of what's going on. It's a change in the time step. Other ways of writing r prime of t, of course, we could do d dt of the vector, or we can write dr dt like that. So what is r prime of t? Is the tangent vector at time t on the parametric curve c. But we do require our vector function to be differentiable at t. And the derivative vector, since it makes a vector, it points in the direction of increasing t. On what I have pictured here, c is increasing as it goes from left to right. So it's increasing as it points to the right. My vector for the derivative right here, this red one, little tiny piece, is pointing to the right as well. Okay. And we would be doing r of t plus delta t as delta t goes to 0. This vector is going back to r of t. A couple of things that we used to write r of t as that, r naught plus tv. When we do take the derivative of r of t with respect to t, r naught doesn't have a t in it. It's a constant vector. V is a direction, a magnitude of direction. The derivative of t is just 1, so we're left with v. So like the derivative of r prime of t is v when we're evaluating at a point. So we can look at r prime of t as starting at r of t naught plus t times r prime of t. How far do we go in this whole direction right here? We are going to use something called the unit tangent vector t. The magnet t, capital T of t is our tangent vector. And the unit vector is the same way we've been doing unit vectors all along. We take the vector r prime of t, we divide by its magnitude. Okay. Let's just take a look at an example. We're going to do 4t squared minus 3 for the x component, 3 sine of t for the y component, and t e to the t plus 2 for the z component. If we take the time derivative, d dt, we can pass it inside to each of them. And when we take the derivative 4t squared minus 3 is 8t. The derivative of 3 sine of t is 3 cosine t. And don't forget to apply the product rule here. First, I took the derivative of t, leaving e to the t alone. And then I took a derivative of e to the t, leaving t alone. Got that. And then the derivative of 2 is a constant of 0. So this is like our v vector. At t equals 0, we can just find out what that v is. R prime is 0, plugging in t equals 0 is 0, 3, and 1. Just plugging, making t equals 0 for each of them. So finding our tangent vector, we take 0, 3, 1 and divide by its magnitude. I've got 1 over root 10 times 0, 3, 1. Or I can move the root 10 inside and do it on each one. Next part, we're going to find the tangent line at t equals 1 for r of t equals the cube root of t for the x component and 1/3 t minus 1 for the y component. On the right side, I'm not going to walk through it, but I did it the old calculus 1 approach. I wrote y as a function of x, just using what we know about parameters, took the derivative, found that tangent line at x equals 1. Let's see if we can get that using the parametric version of what we're doing here. So r prime of t, we take the time derivative of each of the x and y components. Rewriting the cube root of t as t to the 1/3. I have 1/3 t to the negative 2/3 and 1/3 as my r prime of t. Rewriting it with 1/3 factored out and back in radical notation, I have that. So we need to write out our line r0 plus tb. So let's figure out what each of these are. Okay. So if I plug in t equals 1, which is where we're evaluating that, t equals 1, r of 1 is the cube root of 1 and then 1/3 minus 1. We got 1 and negative 2/3. If I do the derivative evaluated at 1, I've got 1/3 times 1 comma 1. So 1/3, 1/3. We'll plug those two in up here. And we get 1 and negative 2/3 plus t times 1/3 and 1/3. Does this agree with what we have up top? I combine them in one vector, doing our vector arithmetic. So if I set x equal to the left side and solve for x, or solve for t, subtract 1 from both sides and then multiply by 3, I get t equals 3x minus 3. We plug that up into our y function. I replace t with 3x minus 3. We work through it, and you will see, in fact, that we do get x minus 5/3. And that'll be it for now. Peace.